Again, we're going to continue with our discussion of Chapter 10. We're in Section 3. I'm going to split this up into two parts because part of it, the next part, is a little bit more difficult. So I know it's hard to do new concepts and then throw in math and then do it virtually instead of in person. So hang in there, have your calculators ready, follow along as best you can, and be sure and send me your questions. So you're familiar with percent, I hope. You see percents everywhere. Percent is used on clothing labels. It's used in percentage alcohol in your hand sanitizer. Percent's used a lot, but who remembers what it really means? Percent means part out of 100, but not everything is in equal increments of hundreds of whatever. So to do percent calculations, as you know, you take the part divided by the total and times it by 100 to get the percent like you would see on this label. Believe it or not, these two solutions are made from two different compounds that only have 3 elements in them, and they're the same 3 elements, but because they are attached in different percents, or there's a different number of atoms is what it turns out, they have very different composition, so or properties, excuse me, and different compositions. So this is an example of the law of multiple proportions, the same 3 elements having the same 3 types of atoms, but in different ratios, different proportions give you different results. So one of them was yellow, one is orange. The one on the left is potassium chromate, and the one on the right was potassium dichromate. Again, just 3 elements, potassium, chromium, and oxygen, but in different proportions. So these numbers that are subscripts that indicate the number of atoms were worked out from early data, from percent data actually. So again, different percent compositions and different properties are the result of different numbers of atoms in those 2 compounds. Of course, they're mixed in water in the 2 Erlenmeyer flasks. So calculating percent mass of an element in a compound sounds a lot weirder than it really is. All you need is the mass data and then the chemical formula, and you're off and running. To calculate the percentage by mass of the elements in a compound, you're going to find the grams of each element. You're going to divide by the molar mass, the total, and then simply multiply by 100. That gives you percent. Percent composition from mass data, this is how these things were worked out. People took compounds, broke them up, found out what they started with, looked at the amount of each of the elements when they decomposed it, and knowing that matter can't be created or destroyed in a chemical reaction, the masses had to be the same at the end and beginning, and from there they worked out the percents. The book has this setup: mass of the element over mass of the compound times 100 if you want to get the percentage by mass of the element. So let's work an example. On your note sheet, please at least write down the masses and percents and follow along as you can. This is an example of a compound that we actually would have made in another lab that we aren't going to be able to do. It looks like a white powder. Turns out it has 2 different elements in it. So when you can decompose 13.60 grams of this, there's magnesium and oxygen. They get 5.4 grams of oxygen, and then that's all they tell you. So this part of chemistry is the worst. It's word problems, your favorite kind of math problems, with stuff you've never seen or heard of before to boot. So hang in there. So this is a bottle representing oxygen. This is a picture of magnesium ribbon. Remember, magnesium is a metal and it can be smashed into really thin sheets. So the total was 13.6. The part from oxygen was 5.4. So you can probably figure out that the rest of it is magnesium. When you do problems, it's always good to write down what you know, what's given to you, and what you don't know, what you're asked to find. We know the total of the compound. We know the amount of oxygen. We don't know how much magnesium, and we don't know either element's percent. So to find the mass of magnesium, you probably already figured it out. It's 8.20 grams. And we simply get that by subtracting the oxygen from the total. To get percent, we're going to take the part that came from each element, 5.40 and 8.20, divided by the total, what we started with, 13.60, and multiply by 100. So again, we know the total, we know oxygen, we've calculated magnesium. Now all we have to do is calculate percent. Grams go away, of course, and we end up with the percent symbol, and it works out to be 60.3. Mass oxygen is 5.40 divided by the 13.60 works out to be 39.7. And most of you smarty pantses know that when you're doing percents, you should get values that add up to 100. Now, with actual experimental data, it may be off just slightly. It may not be exactly 100, but it'll be 99.98 usually. All right, so let's try this one. Mercury 2 oxide, again, is decomposed. We started with 14.2 grams of mercury 2 oxide. So remember the Roman numeral tells us it's a +2. Oxygen's always a -2, so this is the formula. Most of the mass of the sample is mercury. Unsurprisingly, it's a very massive atom, very dense. What's the percent composition of the compound? Well, we got to realize there's another element, oxygen, and the 14.2 minus 13.2 gives you the 1 gram of oxygen. So doing the same process, taking the amount from mercury, the part from mercury divided by the total of the compound, you get 93%. Taking the 1 gram part, because oxygen divided by the total, it comes to 7%, and again, it works out to 100 for the two of them. Sometimes you have to find percent composition from the formula of a compound. So what you need to do is find the mass of each element for 1 mole of your compound and divide by the molar mass of the compound times 100. And the book does these little yellow highlighter box, mass of element in 1 mole of compound. That's your part divided by the molar mass of the compound. That's your total times 100. So we're going to do a calculation with propane. We've talked about propane already. You know, it's a hydrocarbon that many of us have as our home natural gas up here in the foothills. If you don't have a big tank, you might have a gas barbecue grill. So we know that the mass of carbon in 1 mole of propane is 36 grams. Now, if we go out to the pennies place, the hundreds place, that'd be 36.03, but you'll see quickly that's not going to make a huge difference. But the book is just going to the tenths place, so it's appropriate. Hydrogen is really 1.01 grams per mole, but again, this isn't going to affect our results all that much. So 8 and 36 is perfectly fine. They're asking for the percent, so the first thing you've got to do is add these two values up and get the molar mass of propane, which is 44.0, as they've recorded it. And then you just simply take each mass divided by the total of the compound. Mass from carbon is 36 divided by 44 for propane times 100. Same process for the hydrogen, 8 from hydrogen divided by 44 for propane times 100. And we should get, sorry, I kind of went fast through there. You should get a value that adds up to 100. Okay, The next slide has 2 different compounds. You can pause the video and try this for yourself. It's asking you what percentage of nitrogen is in common fertilizers. So NH3 is ammonia gas. It's actually not usually, we don't usually gas our stuff, but there's nitrogen in it. And there's 1 atom of nitrogen in every molecule of ammonia. This one's a little bit trickier. Oops, I should have said pause. Sorry, I'll do that with the next one. So nitrogen's 14.0. I believe it's 14.08 on the periodic table, but for some reason they just use this in the book. Maybe it's 14.01. This next one is ammonium nitrate. That's a very common fertilizer. And you'll notice it has 2 atoms of nitrogen in the compound. So we've got 2 nitrogens, we've got 4 hydrogens, we've got 3 oxygens. So this will give you a little practice at calculating molar mass. You're going to take the 2 nitrogens, 2 times 14 is 28, and then find the total molar mass. So do that as a little practice right now. Pause the tape. So in this compound, the molar mass of ammonium nitrate works out to be 80. Hope you got that. 28 divided by 80 times 100 gives you 35%. Last thing, you can also use percent composition as a conversion factor. So you can calculate how many grams of an element should be in a particular mass of a compound. So maybe you just need a certain element. How do you figure out how much is actually there and available? Well, you can use percents to help you. We're going to go back to propane again, and remember it's 81.8 carbon and 18.2 hydrogen. If I had an 82 gram sample of propane, I could take the percentage times the total of my sample and get the amount of carbon versus the amount of hydrogen. How do you do that? Here's what we start with, the mass of our sample. Here is 81.8 grams per 100, right? We don't always get exactly 100 grams of anything. And you should have 67.1 grams of carbon. You can do the same process for hydrogen. I took the 82 grams for my sample. 18.2 out of 100 is the percent set up as a fraction, and then that works out to be 15 grams of hydrogen. It's actually slightly less. You can see here that 15 and 67 is a little bit more than 82.0, but the process is similar. This, again, is really kind of an awkward way to do the percents. Honestly, I prefer to change the percents to their decimal version. That's what 81.8 divided by 100 would look like. 18.2 divided by 100, of course, and then you multiply by that. Some people get themselves all twisted up in a bunch because they forget to move the decimal the right number of places, so maybe setting the fraction up is better. I don't know. You could also do this by proportions. Blank out of 82 is equal to 81.8 out of 100, and do cross multiplication. You do what makes sense to your brain for calculating. It doesn't matter to me as long as you get the right answer. Hope you're well. Take good care. See you next time.